All right, well, we are back for more. We're making our way through the chapter 20 there, where we're talking about derivatives of carboxylic acids. And last time we ended with the idea, or starting to introduce the idea of orders of reactivity for our derivatives. I probably should have made this a little bit more explicit in the last video, but this chapter 20 here, we're going to talk about how we can interchange between all the different functional groups all the specific carbonyl functional groups that we're going to learn about. So we're going to learn how to go from an acyl halide into an amide, and amides into anhydrides, into carboxylic acids and esters. We're going to try and see how we can interchange all of these different functional groups. Now, some of these aren't direct reactions, right? We can't go directly from an amide into an anhydride. I can't even think of any, I kind of put myself on the spot here. Off the top of my head, I can't really think of any way to do that directly, although I think I already mentioned it, I'm not technically an organic chemist, I'm an inorganic chemist. And so, maybe there's some organic chemist out there screaming at the computer screen right now, like, oh, you idiot, you just do that, right? But the point being this, right, is we're going to learn how we can walk our way through all these different functional groups is what it is, right? We're going to learn how we can go, if we can't go directly from one to the other, we're going to learn how we can maybe take a side step and then get to where we need to go, right? Sometimes taking the direct route is not always the best route either, right? And that will become obvious a little bit in what we mean with that, right? But anyway, we'll get into all that. So anyway, this time what we want to talk about is introduce the broad idea of opening and closing the door, right? And the best way to do that, if you haven't gotten the point yet from the previous videos, is to look at the reactivity of acyl halides. Now, page 910, right, is where I told you guys to go look at this order of reactivity that they have there. And if you want to go ahead and thumb your way over to there now, right, page 922, right, that's where I'm going to be drawing most of my ideas from for this lecture here, right? So take a look at page 922 at the top there, right? So acyl halides. Now, acyl halides are extremely powerful functional groups in the sense that they are very versatile in what they can be turned into. We can turn an acyl halide into an alcohol with reduction. We can turn them into a carboxylic acid. We can turn them into an ester. We can turn them into an amide. We can turn them into an anhydride. We can turn them into a, what haven't I said yet? I think that pretty much covers everything, right? So we can turn an acyl halide into all of the other carbonyl functional groups. Ketones, sorry, I forgot about ketones and aldehydes, right? We can turn them into ketones and aldehydes also, okay? So that's extremely important right there, okay? Understanding that acyl halides are probably our most versatile and diverse carbonyl group that we can use to make any other functional group is going to be extremely important. So we got to do two important things. We got to learn how they're going to react, and we got to learn how to make them, okay? So let's start out by learning how to make them. It's going to be really, really, really easy. So making an acyl halide starts from a carboxylic acid, right? And we can go directly into an acyl halide pretty darn easily using a reagent that we have, let me put an R group here, using a reagent that we've seen before, right? Our buddy thionyl chloride, SOCl2, thionyl chloride. Thionyl chloride is again one of these super, super, super common reagents that we have in pretty much any organic synthetic lab, right? We have seen it used before where we take an alcohol and convert it into a chloride, right? And the mechanism for that, depending on how in-depth your first semester organic professor got with you, it's actually it's not an SN1 and it's not an SN2, it's somewhere in between with that, right? So there are somewhat more complex mechanisms with substitutions that we don't really talk about just because they're specific. We're not really thinking about the word specific. They're very only for one unique instance. I forget, the word is escaping me at the moment, but that's not important. Thionyl chloride is here again, and in essence, we are turning an alcohol into a halide, right? Because if we kind of ignore the carbonyl part, right? Here's an alcohol, and we just turn it into a halide. Now, is the mechanism the same? No, it is not. No, it is not. The mechanism is on page, where is it? on page 918, right? So 918, if you turn to page 918, there's your mechanism for it right there. Do I need you guys to know it? No. Am I going to draw it for you guys here? No, okay? It's right there in your book. You guys can just draw that out. It's not too important for us in terms of what I want to get across to you, okay? I'm not saying it isn't important, it's not vital. This is an extremely important step to recognize, okay? Because this is our way of generating an acyl halide. From an acyl halide, we can make any of our other functional groups very, very, very easily, right? They're all downhill reactions, essentially, right? They're all thermodynamically going to be favored, okay? So, very important, pretty easy. Thionyl chloride is a liquid, right? You can do this as a neat reaction. Sometimes you don't even need a solvent for it. I've done this hundreds of times. It's very easy to monitor the reaction because it kicks off HCl gas. And so you can just, you put a strip of paper over the top of your reaction. When the reaction stops, when the pH doesn't change anymore, then your reaction's pretty much done, right? But anyway, that's a little bit of that's neither here nor there. There it is, okay? That's important thing number one. Now, I'm gonna have to give myself some room here. So let's take, now that we can make our acyl halide, let's do every reaction possible with an acyl halide. You guys ready? We're going to do every single reaction possible. So usually I have 30-minute videos. This is going to be about 30 hours. Ha ha ha, of course not, right? So here's how every reaction is going to work for an acyl halide. The important thing to recognize, or what makes acyl halides unique versus some of the other functional groups, is that you got that halogen there. Now, what have halogens been used for in organic chemistry for us? Well, typically they are there for either two purposes. They're there for substitution or they're there for elimination. Now, we can't really eliminate them in this case because then we end up with these cumulated double bonds, which is not any chemistry that we're ever going to get into, right? And it would be a terrible way to make any of those anyway, but that's a different argument. Well, maybe not terrible, but anyway, that's neither here nor there. What we're going to do is use the halogens here in substitutions, okay? Now be careful, because when I say substitution, you guys should immediately think of two things, SN1 and SN2, okay? Neither one of those is really happening here. The substitution we're doing here is the door mechanism, okay? This is the thing I've been yammering about for the last, I don't know, I think this is like the 5th video in the series here now already. Lots of carbonyl chemistry, right? So for the umpteenth time now, we're talking about a nucleophile comes in, we hit the carbonyl carbon, we swing open the door, the pi bond opens, we close the door, the pi bond reforms and kicks off a leaving group. That is how this mechanism works. It's not a concerted nucleophile comes in and kicks off the chlorine. That's not how it works, okay? Don't draw it like that. It's going to be wrong. The book even emphasized, the book actually does a very good job explaining this. They spend like 5 pages. Well, I'm exaggerating a bit, right? They spend a lot of time explaining this for some reason, and it'd be good to read through that, but I promise you, if you just understand what I said there is nucleophile comes in, pi bond opens, pi bond closes, kicks off leaving group. That is how these acyl halides are going to work. So what is a nucleophile? Well, it depends on what you want to do, right? But before we get into the specific, let's talk about the generics for just a second. So let's bring in Mr. Generic Nucleophile. There it is. And at this point, again, if you don't know what a nucleophile is, shame on you. I don't know how you've gotten this far, right? But please, you have to understand what a nucleophile is, all right? So there it is, Mr. Generic Nucleophile. Okay? Hits the carbonyl carbon, swings open the door, okay? Door open, all right. What does this do? Negative charge on our, on our oxygen. All right, this is our tetrahedral intermediate here. How does this work? Why does this work? Well, there's different reasons for different functional groups, right? At the end of the day, we usually end up trading a negative charge to put it on an oxygen. That's not too bad, right? And as we continue on, we'll throw that negative charge into something that's even better than a minus, than an O minus, right? So there's our intermediate in this case. Now we got to come back and close the door, right? And so door closes. When I make a bond, I've got to break a bond. So I am making this bond. Which bond can I break? Well, there's two options. I can break my bond to my nucleophile. Does that happen? Sure, right? That's the idea of microscopic reversibility, right? We can go back to where we started. That doesn't progress our mechanism any, right? So it's kind of a fruitless step, not that it doesn't happen, right? But if we close the door, we have to break the bond to the best leaving group, to a good leaving group. And it's hard to find better leaving groups than our halogens, right? We've used them so often as leaving groups already in our organic careers that, why would we see them any differently at this point, right? So there it is. There's the magic, right? Cool. So what do we end up making at the end? Well, we could, depending on the nucleophile, right? We could make anhydrides, we could make aldehydes, we could make ketones, esters, amides, any of the other carbonyl groups, right? That is the magic, right, of the acyl halides, right? We can make those into pretty much anything. All we got to do is change the identity of that nucleophile. That's it, okay? That's what page 922 is showing you there. So there it is, okay? So let's go through one of the simpler examples, and we'll come back and talk about some of the shenanigans, I guess. So here we go, right? We will start from the acyl halide, and let's say that we want to make an ester, right? So what is an ester? I remember an ester is where we have this kind of functional group there, right? So what do we need to add into this to make this happen? Well, look at where we start and look at where we end up, right? Well, this is the same, okay, right? That's the same there. So we got to swap out the chlorine for this here, right? So essentially, hopefully you guys catch what I'm doing. I'm just saying, okay, if I need to transform one of these into the other, I need to add this part to it, okay? Which really means I need to add this to it, all right? Because I'm just cutting that off. Now, truthfully, you could add this into there, right? And this would work. That's fine, right? You could just say that your reaction is this right here. And that would get you to the product that you want, right? Wherein you would end up swapping that into make an ester, right? Here's my nucleophile. This is an acyl halide. I identify this as a good leaving group. See if you guys can go through and do the mechanism for that, okay? And that would be just fine, right? This is not an uncommon setup. We've seen these reagents before, something perfectly valid, okay? However, maybe not always the best choice, right? Maybe not always the best choice because, again, let's think about this for just a second, right? In this case, this would be just fine. What is this here, though? That's a really powerful base, right? That's one of our alkoxides, right? So that's a common way that we have of doing elimination reactions, right? So again, these things aren't too selective. If we have some other acidic functional groups around, we have to pay attention to this, okay? Now, we can do this exact same reaction if we just do a little bit of a tweak here and there, right? Sorry, I've been having coughing a lot, so I'm having to try and drink a little bit more here to keep delivering lectures to you guys. So what we're going to do is this, right? So we're going to take these exact same conditions. We're going to help things along by putting some, we'll just take an alcohol now, right? Good old-fashioned alcohol there that, you know, cheap, easy to get to, right? They're not really all that reactive. And then we're going to put in some kind of base, right? And truthfully, we could pick any one of them here. And the book talks about pyridine. Pyridine is this guy here, right? So this is our 6-membered aromatic ring with a nitrogen. It's a good base. It's organic soluble. It's going to be soluble in ethanol, right? So that's a good choice. And this is here to kind of soak up protons is what it is. That's kind of its main goal in this thing, right? Because remember, if we want to get to an O-, right, we basically have to deprotonate that, although that's not what happens initially, okay? I don't want to give this confusion here that the first thing that happens is this deprotonates. No, right? The pyridine is there to kind of soak up some protons along the way, that's all, right? So what do we have here? we have a weak nucleophile, and we have a base to kind of help things going along with it, and that's going to get us to our product here, right? So pick an alcohol, and you can start from an acyl halide. That should be red here. We can start from an acyl halide and get to our ester from this, okay? So alcohol plus some kind of base. We could use triethylamine here also. That'd be a very common reagent that we could do for that too, okay? Nice, okay? So that's how we can make some esters. Not too much else to say about this. It'd be good practice for you guys to go through and do the mechanism, okay? Go through and do the mechanism for this. How's the mechanism going to look? Well, we're going to have attack of a nucleophile at the carbonyl carbon, and we're going to open the door, and then we're going to close the door, and we end up with our product at the end. Okay? So fill in the blank for what you need to there. Okay? Let's talk about something a little bit more awkward then. Okay? But although we'll end up at the same point that you guys probably can already predict as soon as I write it down. Let's bring in our buddy LAH. Okay? And as always with LAH, we finish up with an acid or a water workup. Either way is just fine. They usually use water in there because you really don't want to add acid to LAH, but right? The paper's not going to catch on fire, so it doesn't matter too much. All right, cool. So here it is. So what's going to happen? What do we know about LAH, right? Well, LAH is a powerful base. It's a powerful nucleophile. It will reduce every carbonyl group that we'll practically encounter, right? So acyl halides being the most reactive of our carbonyl functional groups isn't going to be any different, right? It's not like they're going to be spared, right? So same thing's going to happen here, right? So we bring in our hydride, H minus, okay? We open the door. We close the door because we identify a good leaving group. The chloride is a good leaving group. There's this. That is in black, right? Cool. Now what? Well, we have an aldehyde. And remember with LAH, we've always got an excess of this around, right? We got 4 equivalents of hydride for every 1 equivalent of LAH, right? And we've only used 1 of the hydrides. Now we've got an aldehyde around. What's going to happen? Well, the same thing's going to happen again, right? We're going to bring in another H minus, right? Where we open the door, okay? I'll draw it here explicitly for you guys this one time just to hopefully get my point across. There's this, right? Here's the other hydrogen. Okay. Every time we open the door, see if we can close it, right? Are there any good leaving groups here? No, right? If there's not any good leaving groups, we're not going to close the door. And so it's stuck. The door's stuck open, right? So we can't reform the carbonyl. We'll come back in. We'll protonate it with the acid, so we end up with an alcohol, right? So at the end of this, right? With H plus now, then we will end up making an alcohol, right? So we turn an acyl halide into a primary alcohol. Also extremely useful for us, right? Remember, primary alcohols, primary functional groups, we can do a lot with those, right? They're useful for us to do quite a bit of chemistry, okay? But acyl halides all the way to primary alcohol, okay? We can't stop it here. LAH is just going to plow through everything, right? But we can do a little bit of shenanigans. So let's go back. We'll take this, and what we're going to use is, we'll call it LIAL OTBU. Man, that's a word salad. Okay, OTBU3H. Of course we are. That's the only logical choice is to use that. All right, well, let's take a peek at what this is here, right? So remember, LAH is lithium aluminum hydride. So we have lithium, aluminum, and the hydride, Except here we only have one of these H's, and we've got these OTBU things here, right? So let's take a quick peek at what this is. We got an aluminum. There's our hydride, right? And here's what the OTBU stuff is, right? So we got these T-butoxy groups coming off of this aluminum. Now, a couple of quick things. Two quick things to note, right? We only have one equivalent of hydride. That's going to be important, okay? We've got aluminum already bound to some oxygens. That's important too. I think it was a previous video where I talked about how aluminum and oxygen are good friends, right? So that changes the reactivity of the aluminum a little bit, all that kind of stuff too. And the other thing is, these are bulky groups, okay? Steric encumbrance and steric hindrance really does change the reactivity of a lot of different functional groups. And so this reagent here, this derivative of LAH, we could call it, you know, has a couple different things working with it that's going to change how it reacts. Okay? So practically speaking, we can treat this as only having one equivalent of hydride. So you guys, I think, can see where this is already going to go. Well, hopefully you're looking at the book, so you've seen it already, right? Right? But practically speaking, we only have one equivalent of hydride, so, right, we're really only going to do one of these reactions where we only add the first hydride, and so we will end up at the aldehyde, okay? Now, let me say a little bit of caveat. The book, and I know why they do it, I'm not saying the book is wrong. This reagent can still react with aldehydes. So something that's going on behind the scenes is if we were to do this, if we wanted to do this reaction in the lab, we would have to do this at low temperature and really control kind of how we do these things. It's maybe not as clean as a reaction as the book gives the impression for. Okay, that aside, who cares, right? Or we're doing chemistry on paper, right? So if it works, just tell me, Dr. H, and then I can write it on the exam and get points. Okay, that is what I'm telling you, but I'm just letting you know that sometimes the book maybe doesn't paint the best picture for some of these things in reality. Okay, so let me get rid of this and give you guys the practical outcome of this. So if we do this, what we will, we'll put that in red just to kind of continue on here, right? What we will end up is with an aldehyde. Fantastic. Now we can take a acyl halide into an aldehyde. Now remember, whenever you guys are seeing acyl halides, you can even think that there was a carboxylic acid there before this. Because it could go back and ask you guys a question, well, how can we turn a carboxylic acid into an aldehyde? Well, to go there directly, we can, right? But, right, if we have to go through an acyl halide, we can get there also now, right? So we have multiple ways of getting to an aldehyde, depending on the situation that you might need, right? It could be that you're under a certain condition where having a carboxylic acid around is going to interfere with having, adding a base or something like that, right? And so we might have to change things up a little bit, okay? Great example here. Let's talk about another problem that has a similar solution. Okay. We bring in our buddy Grignard's, and the same thing like with LAH, whenever you have a strong base around, you're always going to have to finish it up. Oh, geez. You're going to have to finish it up with water or an acid workup, right? Okay, so Grignards share a similar property as with LAH in the fact that even if we tried to carefully control the sterics, these things are so reactive, not the sterics, the stoichiometry, that even if we tried to, dropwise addition and cold and all this kind of stuff, they're just going to react with any carbonyl compound that's around, right? So in essence, what that means is we have an excess of this Grignard there, right? That's what I'm trying to tell you, okay? But, right, let's take this one step at a time. Let's draw this in red here, I guess, right? So whenever we see a Grignard, right, let's just assume that we have a lone pair and a negative charge on a carbon, just like this. Big shocker, we open the door. Don't forget to count how many carbons you have. Very easy to drop carbons along the way, right? We open the door, we pause, we check, say, can I close the door? Yes, I can. We've got a good chloride leaving group there. Let's do that, right? Okay. Oh, come on. There it is. Okay. Now what functional group do we have? A ketone. Wouldn't it be useful for us just to be able to stop at the ketone and say, there it is? Yeah, except we can't, because what do Grignards do to ketones? Well, they do the exact same thing. They can continue to react, just like with the LAH, right? So what would happen is we would have another equivalent of Grignard come in, right? And we would have this, okay? Which we could then finish up, right? We don't have any more good leaving groups here, so we can't close the door again. I think you guys are hopefully paying attention to that at this point, right? So we would come in with our acid workup, and we would end up with a tertiary alcohol, right? So we add 2 equivalents of the Grignard, there it is, right? 2 equivalents of the Grignard to the starting acyl halide here, okay? So just like what we talked about there with the derivative of LAH, right? We have to develop a different reagent to stop here at the ketone, right? And this is something that you guys have already learned, probably the Gillman reagents, okay? So what is a Gillman reagent? So our Gillman reagents have this generic setup, right? R2CuLi, right? So these copper lithium type species here, right? So where the R group there can be any alkyl group, right? So if we come back and we just swap this out for an ethyl here, so essentially we have 2 of our ethyls attached to the copper there as a lithium salt, right? Now, what's the point or what's the difference or what happens? Well, this in essence softens the nucleophilic and basic nature of that alkyl group. In essence, right, in essence, this is still a carbon with a lone pair and a negative charge. But because it's bound to that copper, it changes the reactivity of this, right? Whereas with the Grignard, it was bound to magnesium, right? It's more of a, we can think of it as almost exclusively as a base or a strong nucleophile. Here, it's definitely more nucleophilic, not as much of a base, not as reactive, not as negative is all I'm trying to say. So what we will do in this case is we will stop at the ketone, okay? So we will end up adding, right, that carbon group right there, and we can end up stopping that at the ketone right there, right? Also extremely useful, right? Perfect. So be careful about which reagents you choose and when you decide to choose those, right? All right, now we'll talk about one last set of reactions here, and then this will be it. This will be, oh yeah, definitely a much shorter video than the normal ones, and that's just fine. So one functional group that which we haven't talked about too much is our amides. Okay, and so we could go back and do the same kind of analysis here. We're basically swapping the chlorine for this NH2, right? If we cut that off, right? We would say, okay, just add this, right? This NH2 with a minus, this amide. That we wouldn't want to do. That's an extremely powerful base, right? In fact, that's how we end up generating our alkynes, right? We've used this reagent before, and on paper, it certainly would work, although we don't, I mean, there's problems with using this stuff, right? There's issues generating it and keeping everything dry, and then side reactions, all this kind of stuff, right? But what we do know about nitrogen is that it tends to be pretty darn nucleophilic on its own, to the point that we can just add, right? We can just add the neutral nitrogen species. So if I wanted to do this conversion, I could just bubble ammonia gas or condense ammonia gas and drop it in there if it was cold enough, right? But we would want an excess of the amine, right? So excess NH3. And that's because, remember, two things to pay attention to or understand about amines is that they are basic and they are nucleophilic, right? And if you think about it, if I'm adding NH3, and here I have to add up with 2 nitrogens, that other hydrogen has to go somewhere. And what you end up doing is making a protonated ammonium compound, right? So we end up precipitating out usually ammonium chloride, right? Where we have NH4 plus with the Cl minus there, right? So if you're making an amide, here's the kicker, right? So if you're making an amide from the acyl halide, add an excess of your amine into it. That's what you guys will need, okay? What's the mechanism for that? Go through and look at it, right? The door opening, door closing, and all that kind of stuff, right? So we can, we will add an excess of alkylamines, right? Ethylamine here, we could add an excess of that, and we could end up generating our amide from that also, right? Not a problem, okay? You'll notice that we always lose a hydrogen in one of these cases, right? Fantastic. So that's kind of the general idea with these, right? How to make acyl halides, okay? How to turn an acyl halide into another functional group. Now there's one thing we didn't talk about, okay? And we'll see if you guys can figure it out. I'm going to ask an empty room, right? Well, we talked about how to go from here to here, right? That's thionyl chloride. How could we go from here to here? Well, the same kind of idea that we've been talking about all along, right? Well, I need to swap out an OH for a Cl. Could I just put hydroxide in there? Sure, right? You could just put hydroxide in there, right? Or you could just add water. That would be just fine also, right? H2O with some kind of base, right? Pyridine again would be just fine, right? Or you could just add in OH minus, right? A slightly basic solution, a little bit of hydroxide in water, that would be just fine right there too, okay? So either one of those cases would work. Well, why would you want to do this? Well, remember, we said one of the useful things of acyl halides is that they're extremely versatile, right? We can turn them into any other functional group. But if we have a carboxylic acid around, right, we have different reactivity. So we have to think about compatibility and all this other kind of stuff that goes with it, right? So we might need to go from an acyl halide into a carboxylic acid is what it is, okay? Fantastic. Next time, I'm going to give you pretty much the exact same lecture, except it's going to be, right, much shorter, right? We're going to talk about anhydrides. Now, anhydrides, I'll go ahead and give you a quick preview. In terms of reactivity, they're like right there. They're almost right there where acyl halides are. Very similar reactivity. We're going to talk about a very similar set of reactions and with just a couple of minor tweaks here and there along the way, okay? But that's it, and I will see you guys in just a little bit.